So the next part we are going to discuss is electrolysis. So as we discussed before, the electrolysis or the electrolytical cell is the reverse way of the galvanic cell. Galvanic cell converts the chemical energy stored in the reactants into electricity or electric energy. So electrolysis is to use an external power source to drive a non-spontaneous redox reaction to go to the right side. So let's read this part. Involves forcing a current through a cell to produce a chemical change for which the cell potential is negative, right? The cell potential is negative means the reaction is non-spontaneous. So if you do not add the external, power source, it will not occur. So we have to use the electricity to force it. So from the perspective of the energy conversion, so here the electric energy is converted into the chemical energy. So let's have a look at these two figures. The left one is a very typical zinc copper galvanic cell. Zinc is the anode. It has the oxidation, right? Zinc lose electrons into zinc 2 plus. So the electron move from the left side to the right side. And the copper is the cathode, so it has the reduction. So it's the copper 2 plus gains 2 electrons reduced into the copper element, copper metal. And then there is a porous membrane here. The overall reaction is zinc reacting with Cu2 plus, produce zinc 2 plus and Cu. So obviously zinc is a more reactive metal than copper. If we analyze from the perspective of the standard reduction potential, zinc 2 plus has a more negative standard reduction potential than the copper 2 plus copper. So in the right side, we use a power source. So I think we may need to analyze what is the positive side, what is the negative side. So in physics, we define, the current is always moving from the positive side to the negative side. So which means the electron will move from the negative side to the positive side. So which means here is the negative side, here is the positive side, right? Electrons move from this side back to the positive side, which means the current will be the opposite from the positive side to the negative side, right? So, so here, the zinc side gain the electrons. So what kind of reaction, can occur here? We need to have something to gain, the electrons, right? So which means on the zinc side, it's the zinc 2 plus from the solution to gain the electron change into zinc, right? There might be another, option is the H plus from the solution gain the electron change into hydrogen gas. We won't discuss, which one is more competitive at this moment. Just give you a sense. We need to have a cation to gain the electron on this side. So no matter which one to gain the electron, it is a reduction. So which means this is the cathode. The left side is the cathode. And in the right side, the electron is lost, right? Lost, and the electron go back to the power source. So that is the anode, because we need to have something to lose electron. So what can lose electron? So the copper can lose electron, change into copper 2 plus. So if we think in the cathode is the zinc to gain electron, let's delete this one. So the overall reaction change into copper react with zinc 2 plus to produce zinc and copper 2 plus. So obviously, as we know, copper is a less reactive metal than zinc. So this reaction is non-spontaneous, but it can occur is because we have the external power source. So this is a typical electrolysis process. But our definition about the cathode and anode are still the same. And you can pay further attention on the electrolysis or electrolytic cells. The cathode actually is connected to the negative side of the external battery or power source. And the anode is connected to the positive side. You do not have to memorize which one is connected to which one. You just use, okay, based on physics, we know electrons move from the negative side to the positive side. But based on the definition in chemistry, anode always have oxidation, so which means you will lose electrons, and the cathode will gain electron to have the reduction. So pay attention to the difference of the external positive, negative side and the internal cathode and anode. So one is defined as the electron movement. Another one is defined as the redox reaction, reduction or oxidation. So I think we already finished this part. So the next part is about the psychometry related to the electrolytic process. So here we may have to review some physics about the current. So current, as we talked about before, it has a unit of ampere, right? Ampere, maybe it's called ampere. Anyway, we use A to represent the unit. So the meaning is 1 coulomb of charge per second. So current is kind of the rate of the electron flow, right? The electron flow. So let's have a look at this question. So let's say 10.0 amperes of current is passed through the circuit for 30 minutes. And the circuit is going through a solution containing copper 2+. The question is asking how many grams of copper is deposited on the electrode. So which means the reaction is copper 2+ gain 2 electrons, turned back into copper, right? So this is kind of, we need to convert the current, the time, the number of electrons into the mass of copper, right? So I think first we can do some calculation. So if we know the mass of the copper, we can divide it by the molar mass to calculate how many moles of copper is produced. And use this, we know if we times 2, we can get how many moles of electrons. So this is the moles of the electrons, right? And last time we introduced a concept of Faraday's constant, right? Faraday's constant means for 1 mole of electron, how many coulombs? So we can use this amount of the moles of electron times the Faraday's constant to get how many electrons. So by using the Faraday constant, we can get the number of electrons. So if we get the number of, not the number of electrons, is the coulomb, is the charge of the electrons. If we get the charge of electron, and then we can use the current times the t, the time, to get the same charge as well, which means the charge, going through the circuit is 100% used to, convert the copper 2+ into the copper. This is the ideal situation, but in calculation, in theoretical calculation, we assume there is no energy lost. There's no electron lost. There's no electrons used to drive any other side reactions. So we can make this assumption and do the calculation. Okay, then let's recall the process from a reverse way about how to solve this kind of stoichiometry problem. So we have the current and the time, which means we have the I, we have the T. By times these two together, we got the Q. The Q is the quantity of charge in coulombs. And then by dividing the Faraday's constant, we got the moles of the electrons. And then we can use the number of electron transferred during the process is 2 in this case, 2 electrons. So we divide by 2, we got the moles of the copper, and then we multiply by the molar mass of copper. Finally, we got the mass of the copper. So actually, this is the contribution made by Faraday. So he successfully connected the mass of the metal with the physical spot, kind of the current, the time. So this is called the Faraday's law of electrolysis. So the final equation is like this. So the moles of the electrons, Ne, equals to the coulombs over the Faraday's constant. So the coulomb equals to, the coulomb is the unit of the charge, equals to the current times the temperature. So it's IT over F. And then we can further use the moles of the electrons into the mass of the metal. So let's have a look at an example. So it's an alloy made by copper and silver. So it dissolved in nitric acid. So obviously the copper will be oxidized into copper 2+, and the silver will be oxidized into the silver plus. And then the mixture of the solution is electrolyzed. Electrolyzed to redeposit all of the metal ions as the elemental metals. So basically, copper will gain 2 electrons into copper, and Ag plus will gain 1 electron into Ag, right? So it requires a current of 0.150 ampere for 1429 seconds. The question is asking for the mass percent of copper in the alloy, right? So let's try. So first we can calculate the Q equals to I times T. So we got 0.150 ampere times 1429 seconds. So let's use the calculator to get the results. Okay, we got 214 coulomb, since we only have 3 significant figures. And then we can get the moles of the electron by using Q over F. So it's 114 coulomb divided by 96500 coulomb per mole. So we got divided by 96500. We got 2.22 times 10 to the power of -3 mole. So this is the number of electrons. But we need to pay attention. Each copper 2+ gains 2 electrons, but each silver plus only gains 1 electron, right? And another value we know is the total mass of the copper and the silver. So I think it's time for us to set up, 2 unknowns, X and Y, because we have 2 independent equations, right? So let's say the moles of copper is X, the moles of silver is Y. So we can check the molar mass of copper and silver to set up an equation for the total mass, which is 63.5, if I didn't, remember wrong. This is the molar mass of copper times X plus 108. This is the molar mass of silver. Y equals to 0.100 gram. And another equation we can make is X times 2, because each copper 2+ gains 2 electrons, plus Y times 1, right? Should equal to the total moles of the electrons, which is 2.22 times 10 to -3. And then we can solve this 2 linear equation group and get the X and Y. And then I think the next is easier. You can just convert into mass and get the mass percent of the copper in the alloy. So this is kind of the general method. So you guys can, finish the calculation by yourself, check with the answer key to see whether it's correct or not. So let's have a summary. So the potential supplied to an electrolytic cell must be at least as great as that of the cell reaction to be reversed. This makes sense, right? If it's 100% efficient, which means they are the same, right? But if there is some energy lost, right? For example, some electrons or some current is not used to do the electrolysis reaction we need, and then it needs to be even higher than the cell potential. And if there is more than one reducible species in the solution, the species with the greater potential for reduction is preferentially reduced, right? I think this also makes sense. For example, in the solution, if we have both zinc 2+ and copper 2+ with the same concentration, let's say both are in standard state, 1 mole per liter, and then which one will gain the electrons first? It should be the one with a larger reduction potential, which is the copper 2+. Why? A larger reduction potential means easier to gain electrons, right? Keep this in mind. Electrons always move from a lower potential to a higher potential. A larger potential means easy to gain electrons. So this one is preferred. So the same principle applies to the oxidation. For example, if you have zinc and copper metal to lose electron, so zinc will lose electron first. But everything is discussed at the standard state, okay? Because if the situation is not a standard state, it's more complicated. The next part is about some examples of electrolysis. What will be produced on the cathode, what will be produced on the anode. So first, let's have a look at the electrolysis of water. This is a very well-known experiment. We can use this experiment to confirm the formula of water. So basically, we put the 2 electrodes in a upside down test tube, and the test tube is fulfilled by the water. Typically, we add some electrolyte in the water, such as sulfuric acid or sodium hydroxide, because pure water is a poor conductor. It barely, it's poorly conduct electricity. So, you cannot really do the electrolysis in the pure water. So this is why we add some electrolytes. And then we have a external power source. This is a negative side, this is the positive side. As we analyzed before, the electron will move from the negative side to the electrode. So this electrode will have the reduction. So if it's a reduction, it will be the cathode. And obviously, this one will lose electron, and the electron will move back to the positive side of the battery. So this side will have losing electron, have the oxidation, and then it is the anode. So we can try to analyze, what is the reaction on the anode. So we need to have something to lose electron. So what can you lose electron in water? Lose electron will have the oxidation. So obviously, the -2, the oxidation number, -2 oxygen will be oxidized by losing electron. So O2 will be produced. And then the H+ will be, remain. So if we balance reaction, it will be like this. So it will lose 4 electrons because there are 2, oxygens. Each of them change from -2 to 0, which means it loses 2 electrons each, right? And on the cathode is a reduction. So which one will be reduced? It gains electron. So obviously it will be the +1 hydrogen changed into hydrogen gas. And then the hydroxide is left. So if we balance it, it will be like this, right? So the overall net reaction is water change into hydrogen gas and oxygen gas and 2, 2, 1. By the way, if you add these two reactions together, you may need to multiply by 2 to the second one because you want to keep the electron transfer the same, right? The number of electron lost equals to the number of electron gained. So finally, you got 2 moles or 2 equivalents of hydrogen gas and 1 equivalence of oxygen gas. So as you can see, the volume here, this is 2H2, this is 1O2, right? It makes sense. So, in the, I think, 18th century, scientists, chemists use this kind of method to confirm the formula of the water. There is a related question. In practice, however, if platinum electrode connected to a 6 volts battery are dipped into pure water, no reaction is observed. Why? Because it's pure water, right? It's pure water, so it does not conduct electricity. So this is why no reaction is observed. So this is kind of a introductory example. Let's try to have a few more complicated examples. So let's say the electrolysis of mixture of ions. If we have a solution with these 3 ions, probably is an alloy dissolved in nitric acid. So if the voltage is initially very low and gradually turned up, in which order will the metals be plated out on the cathode? So cathode will have the reduction, right? The reduction is kind of the metal cation gaining the electron change back into the metal. So they have different, standard reduction potential. So the question is asking, which one will gain the electron first? So obviously, as we discussed before, the one with the largest, the most positive standard reduction potential will gain the electron first. So which means the Ag will plate out first as the potential is increased, and then followed by the middle one, the copper, and finally the zinc. Let's have a look at one more example to predict the products of electrolysis of colorless Ki, potassium iodide, with some phenolphthalein, which is an indicator added on the we need to analyze what is the reaction on the cathode, what is the reaction on the anode. So this is a experimental picture. I think you see, in this side, there are a lot of bubbles, colorless bubbles. It's not that clear, but I think we can still see the bubbles. And at the same time, it changed into pink, a little bit purple. And in the right side, there are some kind of reddish brown stuff produced. So there are a bunch of questions we need to analyze. Which side is the cathode, which side is anode, what is the reaction on each, right? First, what we can see, the red color, the pink or purple color means there is hydroxide produced, right? And the bubbles probably is the hydrogen gas, because when hydroxide is left, hydrogen gas is produced. So from water to hydrogen gas, this is a reduction, right? Because the oxidation number changed from +1 to 0. This is a reduction. So which means the left side actually should be the cathode. So this side will be the anode. So on the anode, there will be oxidation. So in the Ki solution, we have K+, we have iodide, we have H+, we have hydroxide. Which one will be oxidized? So based on the experimental observation, I think we can conclude is the I- is oxidized. So the I- lose 2 electrons, change into I2, And I2 has color, right? That is the only one, the only species which might have color in the system. And actually, this kind of reddish brown stuff is not just I2, it's the I2 bind with some excess of I minus turned into the triiodide. So this is the reddish brown stuff. So if we summarize, this is the reaction on the anode, and on the cathode, we already figured out is the evolution of hydrogen gas from water. Water gain 2 electrons, turned into hydrogen gas and 2 hydroxide. And hydroxide will make the phenolphthalein to be pink because phenolphthalein has a pH range of 8 to 10. If the pH is higher than 8, it will be pink. If it's higher, it will be red, right? So this is somehow, we guess the reaction based on the experimental results. So can we find some theoretical support about the results? Let's try. So on the anode, we need to have something to lose electron. So there are 2 species which have the ability to lose electron. One is the iodide, another one is the hydroxide. So the hydroxide can lose electron, change into the O2, right? O2. So which one will prefer to lose electron? You may have to check the standard reduction potential, right? So this is quite similar to what we discussed here. Which one will gain the electron, first, right? A common used way is to compare the oxidizing ability of the products. And we know O2 has a kind of similar oxidizing ability with Cl2, chlorine gas. And obviously, based on the periodicity, chlorine gas is much stronger than I2 as an oxidizing agent. We can go back to the standard reduction potential table to confirm this. Let me do some clean up here. Let's try to find, the halogens and also the water. Cl2 is here, 1.36 volts. Br2 is here, 1.09. I2 is here, 0.54. So which means down the group, actually F2 is here. Down the group, the standard reduction potential is getting smaller, which means the halogen elements, it's harder to gain electrons. Or we can say the halogens is getting weaker in terms of oxidizing ability, right? I think this is easy to understand because, when the size of a halogen is getting larger, the nucleus is weaker to gain electrons, right? This trend is similar to the electron activity and also consistent with the first ionization energy. And then let's have a look at where is water. So water is here. So you see water is kind of comparable with, the chlorine gas. So this is why O2 is much easier to gain electrons compared to I2. So which means the I minus is easier to lose electron compared to water. Make sense? So which means as a oxidizing agent, as a reducing agent, I minus is stronger than water. So I minus will first, lose electron to change into the I2. So you might ask, may I have to, remember all of those values, all of those orders? Not necessary, but you may need to have some sense, because all of the electrolysis or most of them are in the aqueous solution. So the water O2 half reaction, the H plus hydrogen reaction will be the reference, will be the standard. So you may need to know what kind of half reaction are above the O2 and which kind of half reaction are below the H2, right? And then you can figure out when electricity is passing through the aqueous solution, what will be the reaction on the cathode and on the anode. So if we go back to the Ki system, on the on the cathode, we also have two competitive ions. The first one is the K plus, another one is the H plus, right? So at standard state, I think it's very easy to conclude the H plus is much stronger to gain the electrons, right? Because the metal potassium is so more reactive, right? So H plus is much stronger. Although the real situation is not a standard state because the H plus probably is at around 10 to the negative 7 mole per liter. It might change this value because it's non-standard state. But still, since the potassium is so much more reactive, so even the H plus is much smaller, the H plus still win the competition. And in our next class, I think we can do some further quantitative calculation to support even when the H plus is only 10 to the negative 7 mole per liter, it still can win the game. Okay, let's leave this to our next class. So this is a very typical experiment. I think you guys can take some notes and further analyze it by yourself. Oh, we are approach to the end. So let's have a summary. When an electrolyte solution is electrolyzed, what competes with the cation dissociated from the electrolyte to gain electrons on the cathode, I think is the water, or more specifically is the H plus, right? The H plus from the water will compete with the cation. So which one will win the game? It depends on the potential, right? So the standard potential can give us some reference. If the standard potential are kind of close, which means we may need to further compare their concentrations. And the hydroxide, also from water, will compete with the anion to lose electrons on the anode, which is largely determined by the standard electric potential of the half reaction or the OX-RED pair, the oxidation reduction pair. Let's have a look at the final extension question. Predict the products of electrolysis of a colorless silver fluoride on the cathode and anode respectively. So let's try. Cathode, we still have the reduction. So reduction, we have Ag plus, we have H plus, right? These two can both, gain electrons. So which one will win? You can either check the standard potential. You can also use your experience because we know silver is a very unreactive metal, which means it's a post-hydrogen metal. Post-hydrogen metal means the standard reduction potential is positive, is greater than the SHE, the standard hydrogen electrode. So which means the Ag plus is stronger is easier to gain the electrons. So on the cathode, we will get the silver plus, a silver metal plated. And on the anode, it will be oxidation. So we also have two competitors. The first one is F minus to lose electron, change into fluorine gas. The second one is the water will lose electrons, change into O2 and H plus. Four electrons, right? Which one will win the game? We know if you check the potential table, the fluorine has the highest standard reduction potential, which means fluorine gas has the strongest ability to gain electrons, which means the fluoride has a weaker ability to lose electrons. So which means the water will win the game in this case. So what we will get is silver on the cathode and O2 on the anode. What will be remain in the solution will be HF, right? The H plus from here, left from the anode, and the F minus left in the solution, right? In the solution. So we get HF. So I think we can practice more about the electrolysis, what kind of products will be produced on the cathode, on the anode. There are a bunch of practice problems like this in the past US NCO, both in the local and the national. So you guys can take some time to work on this. Yeah, that's the end of electrolysis. So I will see you guys on Sunday and continue to talk about the potential at non-standard state. See you.